Pipe Materials versus Pipe Services, Engineering Overview, Comparing Materials and Services in Pipe Engineering. Purpose of the presentation. This section introduces the overall purpose of the engineering presentation, which is to provide a structured and professional overview of how different pipe materials are selected based on corresponding pipe service conditions. It explains that in the oil and gas, utilities, petrochemical, and industrial sectors, material selection is a critical engineering decision that affects reliability, safety, cost, and long-term maintainability. The content further emphasizes that engineers must evaluate mechanical strength, corrosion resistance, temperature suitability, and compatibility with transported fluids to ensure successful plant operation. It also highlights that the presentation will walk through common materials, including carbon steel, stainless steel, duplex alloys, nickel alloys, plastics, and composites, and match them against typical service categories such as hydrocarbons, utilities, firewater, chemicals, and seawater systems. In addition, the narrative outlines the expectation that diagrams, real images, and reference illustrations support conceptual clarity for engineering teams, project stakeholders, and decision-makers. This introduction sets the tone for a professional technical learning session designed to improve understanding and application of engineering judgment in real projects. Presentation Roadmap. This slide provides a detailed roadmap of the presentation structure. It explains that the session will begin with design philosophy and fundamentals of piping material engineering, followed by an in-depth look at each major pipe material category. Subsequently, the presentation will address service-based engineering requirements, compare material capabilities, highlight risks related to improper specification, and introduce relevant industry codes and standards. The roadmap also indicates sections on engineering best practices and a conclusive summary to reinforce key technical takeaways. This ensures the audience understands both the flow and the rationale behind the sequencing of topics, enabling them to connect individual technical discussions to the broader engineering decision-making process. Basics of material selection. This slide discusses the fundamental engineering principles behind selecting pipe materials for process and utility applications. It introduces concepts such as allowable stress, corrosion allowances, toughness, code-mandated minimum requirements, and the impact of operating pressure and temperature on material performance. The narrative explains how early material selection influences procurement cost, welding procedures, fabrication methods, and long-term maintenance strategies. The content also covers considerations like erosion resistance, compatibility with fluid chemistry, internal and external corrosion concerns, and the economic trade-offs between low-cost materials with higher maintenance needs versus premium alloys with long service life. These fundamentals help engineers form a strong foundation prior to evaluating actual material categories. Characteristics and applications of carbon steel. This slide describes carbon steel as the most widely used material category in piping systems due to its strength, cost-effectiveness, and broad availability. It elaborates on grades such as ASTM A106, A53, and API 5L, which are commonly applied in hydrocarbons, steam, water, and general utilities. The narrative discusses corrosion susceptibility, the need for internal coatings or corrosion inhibitors in aggressive environments, and typical limitations in sour service or high chloride systems. It also addresses mechanical robustness, weldability, and standardized manufacturing, making carbon steel suitable for extensive pipeline networks and industrial plants. This slide emphasizes that while carbon steel is versatile, engineers must always evaluate corrosion mechanisms to ensure long-term reliability. Low-temperature carbon steel, LTCS, use in sub-zero and cryogenic conditions. This slide focuses on LTCS grades such as ASTM A333 Grade 6, engineered to maintain toughness and prevent brittle fracture at low temperatures. The content explains the metallurgical adjustments that improve impact resistance, making LTCS essential for LNG systems, cold climate installations, and refrigerated hydrocarbon services. It highlights that selecting LTCS is critical in preventing catastrophic brittle failures during depressurization or emergency shutdowns. Engineers must verify minimum design metal temperature, MDMT, and perform Charpy impact testing as required by ASME B31.3. The narrative emphasizes that LTCS is used when carbon steel would otherwise lose ductility, ensuring system integrity under cold conditions. Stainless steel, 304 and 316, corrosion-resistant applications. This slide explains that stainless steel, particularly 304 and 316 grades, offers excellent corrosion resistance due to its chromium-rich passive oxide layer. SS304 is suitable for general corrosion environments, while SS316, containing molybdenum, offers superior chloride resistance, making it preferred in marine, brackish water, and chemical handling applications. The narrative covers stainless steel's benefits in hygiene-critical industries such as food processing and pharmaceuticals, as well as its higher cost and fabrication considerations. Additionally, it explains susceptibility to chloride stress corrosion cracking, galvanic interactions, and the importance of selecting the correct grade for long-term performance. Duplex and super duplex stainless steels, high-strength corrosion-resistant alloys. This slide describes duplex and super duplex alloys, emphasizing their unique mixed microstructure of austenite and ferrite that provides exceptional strength and chloride stress corrosion resistance. They are widely used in offshore platforms, subsea systems, and desalination plants, where standard stainless steels may fail due to aggressive chlorides. The narrative highlights their fabrication challenges, heat treatment sensitivity, and higher material costs. Engineers must assess PREN values, welding procedures, and environmental factors to ensure the correct duplex grade is applied for seawater, injection water, or high-pressure subsea conditions. Nickel-based alloys, extreme corrosion and high-temperature performance. This slide reviews advanced nickel alloys such as Inconel, Monel, and Hastelloy. These premium materials are used in highly corrosive chemical services, high-temperature applications, and areas where equipment failure is unacceptable. The narrative explains their exceptional performance in acidic environments, high-stress conditions, and thermal cycling. However, they come with significantly higher cost and specialized fabrication requirements. Engineers must justify nickel alloys through rigorous risk assessment, life cycle analysis, and process safety considerations to ensure their selection aligns with project requirements. Galvanized iron, GI, utility and firewater applications. This slide covers the use of galvanized iron piping, which involves carbon steel coated with a protective zinc layer. GI is commonly used in building services, utility water, and some firewater networks due to its low cost and corrosion protection. The narrative discusses the limitations of zinc at higher temperatures, incompatibility with hydrocarbons, and risk of coating degradation over time. GI remains suitable for non-critical service conditions but requires careful evaluation to avoid premature corrosion or flaking in industrial environments. Copper and copper alloys, instrumentation and utility applications. This slide explains the advantages of copper in small-bore instrumentation, HVAC refrigerant lines, medical gases, and air systems. Copper provides excellent thermal conductivity, corrosion resistance, ease of bending, and reliable joining methods. However, the slide also highlights limitations such as reduced pressure capability compared to steel, vulnerability to ammonia-induced stress cracking, and higher cost relative to plastics. The narrative reinforces that copper is typically used in specialty or non-process lines rather than core industrial piping systems. PVC, CPVC and UPVC, plastic piping for low-pressure systems. This slide describes polymer-based piping such as PVC, CPVC, and UPVC, used in low-pressure chemical drainage, water distribution, and non-hydrocarbon services. It explains key advantages including corrosion immunity, lightweight installation, and cost-effectiveness. However, temperature limitations, UV sensitivity, and incompatibility with hydrocarbons must be addressed. Engineers must verify chemical compatibility, fire rating, and joining methods for safe application in industrial environments. HDPE and PE, flexible piping for buried and distribution systems. This slide explains the use of HDPE and PE pipes in water, gas distribution, and underground utilities. Their flexibility, fused joints, and resistance to soil movements make them highly reliable in buried installations. The narrative discusses their chemical resistance, pressure classes, and installation techniques such as butt fusion and electrofusion. Limitations include reduced performance at elevated temperatures and the need for controlled installation procedures to ensure weld integrity. GRE or GRP composite piping, corrosion-resistant composite systems. This slide describes GRE and GRP composite systems made from glass fibers and epoxy resin matrices. These materials offer excellent resistance to seawater, chemicals, and firewater corrosion. They are widely used in offshore platforms and desalination facilities. The narrative also highlights challenges such as susceptibility to impact damage, strict installation procedures, and UV sensitivity. Proper engineering evaluation ensures composite piping is used where corrosion is the dominant risk driver. Concrete and RCC pipes, structural piping for civils and drainage. This slide focuses on concrete and RCC pipes typically used for stormwater, sewage, culverts, and large diameter drains. Their high compressive strength and long service life make them ideal for non-pressure applications. The narrative highlights their weight, installation requirements, joint sealing considerations, and unsuitability for high-pressure fluid systems. Civil utility networks rely heavily on concrete pipes for structural load-bearing performance and durability. Classification of industrial piping services. This slide categorizes common industrial piping services: hydrocarbons, liquid and gas, utilities, air, steam, water, chemicals, cooling water, seawater, and firewater. The narrative explains that each service category imposes different corrosion, pressure, and temperature requirements. Understanding these categories is foundational to determining the appropriate material specification. Engineers analyze fluid composition, operational cycles, phase changes, contamination risks, and external environmental exposure when classifying services. Material selection criteria, engineering factors affecting material choice. This slide discusses the primary criteria used in material selection: design pressure and temperature, corrosion mechanisms, mechanical loading, erosion, fluid chemistry, and life cycle economics. It explains how codes like ASME 31.3 define minimum allowable stresses and material limits. Engineers must evaluate environmental conditions, insulation interactions, fireproofing needs, and compatibility with fabrication processes. The narrative emphasizes that thoughtful material selection ensures safety and reduces long-term operational costs. Material versus service comparison, typical material, service mapping. This slide provides an analytical comparison of how pipe materials align with various services. Carbon steel is typically used for general hydrocarbon service, stainless steel is selected for corrosive or hygienic applications, duplex is chosen for seawater or high chloride environments, GRE is applied where corrosion dominates, and plastics serve low-pressure utilities. The narrative explains the trade-offs between cost, performance, installation complexity, and long-term reliability in different industrial settings. This comparative understanding enables engineers to make informed decisions. Risks of incorrect material selection, engineering and operational hazards. This slide highlights the consequences of selecting incorrect materials, including rapid corrosion, leaks, rupture, safety incidents, unplanned shutdowns, contamination, and extensive maintenance costs. It explains how mismatched materials can cause galvanic corrosion, stress cracking, thermal failure, and structural degradation. The narrative stresses that process safety relies heavily on correct material specification, making early engineering diligence essential to avoid costly failures. Applicable international engineering standards. This slide outlines major standards governing piping design and materials, including ASME B31.3, process piping, B31.4, pipeline transportation, B31.8, gas pipelines, ASTM material standards, and API specifications. It explains that compliance ensures minimum safety requirements, material qualification, testing procedures, and fabrication quality. Engineering specifications from clients often build upon these standards, adding additional requirements for harsh environments or specialized processes. Engineering best practices, approaches for reliable material engineering. This slide presents best practices such as conducting corrosion assessments early in design, performing material fluid compatibility reviews, consulting vendors for alloy suitability, verifying heat treatment procedures, evaluating lifecycle cost rather than upfront cost alone, and documenting all engineering decisions. It emphasizes cross-discipline coordination between materials engineers, process engineers, and fabrication teams. Following these best practices significantly enhances system reliability and operational safety. Key takeaways. The concluding slide reinforces the central message that material selection must always be driven by service conditions, operational requirements, and safety considerations. It summarizes the importance of understanding each material category, recognizing limitations, adhering to engineering standards, and applying sound judgment throughout the project lifecycle. The narrative encourages engineers to continuously expand their knowledge of materials to ensure safe, efficient, and cost-effective piping systems.